Welcome to Academic Paper Cuts, the podcast where we sit down with researchers and the papers they've written and get them to break down the research so anybody can understand it.
For our first episode, we have Dustin Pulver. Dustin is currently a machine learning engineer at Verizon. In Dustin's Master's of Computer Engineering at Queen's University, he built a machine learning model that predicts people's mental effort from their brain waves. We will be asking him about the paper he wrote on this episode.
Some of the exciting technical topics he explains to us are EEGs, machine learning, transfer learning, and transformers in machine learning. We were pretty clueless to start, but have a better understanding now.
Dustin also happens to be one of our best friends, so enjoy us hanging out, laughing, and learning about his paper.
Dustin Pulver, welcome to the Academic Paper Cuts.
Hello.
Thanks for coming on the first honorary podcast of this series. So for everyone in the audience, Dustin Pulver currently works as a machine learning data scientist at Verizon. And he's actually done some research in the past at Queen's University when he was working on his master's on a lot of topics in the place of like psychology and brain signals and things like that. And so today we're going to talk about Dustin's paper, and we're going to get him to just explain it to us like we are little kids so we can understand it.
Yeah, it's my pleasure to be on the pod and my honor to be the first guest.
Awesome.
Yeah.
Well, let's just start at the top here. The paper's called EEG-based Cognitive Load Classification using feature-masked autoencoding and emotion transfer learning. How'd you come up with that name?
I mean, ChatGPT definitely helped. We consulted it for some title advice, but it was really my professor. I mean, he's done this so many times, he knows how to write a title.
Do you know the title by heart?
Actually, it took me a while to actually know it by heart. I honestly don't know if I know it by heart anymore, but
at one point you did.
Yeah.
Okay, good. So we wanted to do a little thought exercise to start off. Aaron is going to go ahead and describe the paper in his own words, and then we want you to describe it in your own words.
Sure.
And then we can jump into the understanding. And also, just before we jump in, this paper's link is available in the bio of this episode. So if you want to pause here, give the paper a quick glance or a thorough read, and then jump back in, you're more than welcome to do so.
Yeah, and rip me apart however wrong I got this. Okay, basically from reading the paper, top made a lot of sense to me. Everything in between, I had no idea. The end made sense, but I think it's basically you took a bunch of patients and you hooked up wires to their heads so that you could get electrical signals, which are this EEG thing that you talk about. And then you asked them what their emotions were, or someone else asked them what their emotions were. Then you took both of those data sets, the emotion, turned it into this cognitive load measure, how difficult you're thinking or something like that. And then fed this into this AI machine learning system that you created so that it could take that data of cognitive load brain signals and tell you what someone's actual cognitive load would be from that. And however the machine learning stuff in it actually works, I have no idea, but I'm hoping you're going to tell us.
Okay, that's your explanation?
Yeah.
Okay, so yeah, that was pretty good. One thing to note is, so there were 3 data sets used, and we'll get into it, but 2 of them are publicly available data sets, and one of them was conducted by a PhD student at Queen's. Her name is Prithila, also an author on the paper.
Is that the CL Drive?
Yeah, that's CL Drive.
Okay. Yeah.
Okay, so maybe I'll give my, brief explanation as to what it is. The idea, and if you can sort of go through the title, so EEG-based Cognitive Load Classification. EEG is a sensor you wear on a head. It's non-invasive, and it detects electric signal in the brain. And the idea is to be able to classify cognitive load based on EEG signal. And the reason you would do that, or the importance of it, is cognitive load it's a subjective measure of the mental effort or resources required to complete a task. So this is important in a variety of different sensitive domains usually. That's where it would be important. One example would be in a driving situation. It has been shown that high levels of cognitive load could lead to increased risk of accidents.
Meaning if people are using a lot of mental effort while driving,
yes.
Does that mean they're distracted or they're putting that effort into driving?
Well, it's just saying that high cognitive load levels increase the risk of accidents.
So
whatever that means.
Mental strain increases your
which
risk.
makes sense. It's logical.
Yeah, very
like
logical.
if you're making a left turn at a light, you're going to be thinking harder and in turn probably more likely to get in an accident. Another situation would be a surgeon during surgery. If his cognitive load level is high, this could lead to, I don't know, maybe an error or something.
Okay.
So the idea being that if you're able to classify high levels of cognitive load, you could alert the person, say maybe you should take a second, you have high cognitive load, you're at a higher risk of an error occurring. So that's I guess, motivation. We want to be able to classify cognitive load from EEG signal.
And what does that like feel like for the person? Is it like a headache's coming on, or it could be weak or strong?
I don't know. I mean, so I guess a little more context, like I was in computer engineering, studying machine learning. I'm no expert in psychology or whatever, I don't know, field you would consider cognitive load being, psychology.
Yeah, probably psychology.
I don't really know much to anything besides the research I put into the paper. So I'm not an expert in that. It's an interesting question. So that's the motivation of the paper, why we would do it. Then I guess if we go back to the title, EEG-based Cognitive Load Classification using featured mass autoencoding and emotion transfer learning. So that's two things there. Yeah, so featured mass autoencoding, we don't need to go into really super detail as to what that means, but the idea is to use transformer architectures. And so what a transformer architecture is what you would find with ChatGPT or other large language models that almost everyone's now aware of. Those are transformer architectures. And the idea is to use transformer architectures to classify cognitive load. One thing to note is that transformers require a large amount of data to be trained. ChatGPT was trained on the entire internet. So yes, we did train these models ourselves. And so one thing is that biosignals like EEG, there's not large amounts of them on the scale of the internet. They're costly to collect biosignal data sets. It's not easy. There's, human concerns and ethical concerns as to collecting the data. So it's a lot harder to collect the data. And so the last part of the title, emotion transfer learning. Transfer learning is the idea that you can train a model to do one task, and then take that knowledge and transfer it to a different domain. So we use that idea of transfer learning. We train the model on emotion, because there were more emotion-related data sets of EEG online, so publicly available. So that gave us the ability to use larger amounts of data, pre-train it on emotion, and then be able to classify.
So in an ideal world, you have the EEG and the cognitive load data, but you didn't. So you needed to work around that by using this transfer learning method to take something that we had a lot of data on, which is EEG and emotions, and then you kind of turn that output from emotion to cognitive load.
Yeah.
So what is the procedure of determining if that mapping of emotion to cognitive load is accurate? That seems sort of subjective for an academic environment like this.
And how did you actually do like that mapping? Like how do they?
Well, it's not really what it is. So emotion or transfer learning. You could think of it, a better way of understanding it would be like how vision models are trained. So convolutional neural networks, they They could do image classification. They're mainly used for image input.
Meaning image classification, meaning, yeah, I see a picture.
Is it
you
a
tell me
dog
is it
or
a cat? Yeah.
Yeah. So if you take that example, you pre-train the model on 1,000 different random objects. Could be any objects, books, people, planes, street signs, random objects. You train on a very large data set of these random objects, and it's able to, the idea is that by training it on all these objects, the model has learned basic understandings of objects from image. What edges are and what their significance are, what color is and how is it significant. So the model has learned these ideas from training on these large amounts of data. And so there is similarity between these random objects and, let's say, the main task, the downstream task, is being able to classify between cats and dogs, right? So it's already understood maybe what texture means, like fur, right? Being able to determine if it's a cat or a dog. So you pre-train on the stuff, it gains that knowledge, and you transfer that knowledge to the downstream task.
Which would be like classifying
cats or dogs.
But if you trained it on cats and dogs, would that be classifying, I don't know, horses versus people?
Yeah, that would be a transfer learning.
Okay.
Right? So if you had a model that was trained to classify cats and dogs, you could use transfer learning to detect horses, right? And because they're related, because cats are also animals, right? So the model has understood things about animals in general.
But could it do stop signs from that?
So that's the thing. You can try to use transfer learning, right? And it's more effective when the pre-training task is similar to the downstream task.
And cognitive load and emotion are similar.
Yes.
So did you go into writing this paper thinking, I'm going to classify cognitive load, so I got to find something similar? How did you end up in...
Yeah, so I guess how we started was we knew transformers were good tools to use on spatial temporal data sets that or data sources that have spatial temporal relations.
Meaning?
Yeah, so cognitive load has this, but another explanation would be video has spatial temporal relations. Temporal means over time. So each video frame, right, there's relations between what's going on in frame 1 and frame 10. And then spatial relation would be what's going on in the relationship between an object in the top left and the top right, or how it evolves over time, right? So transformers are really good at capturing that. And so language also has that. And so we've seen the success from transformers, especially in language with ChatGPT, that it's very good at doing these things.
So in your case, is it the location in the brain and then how that evolves over time?
Yeah, so if you look at the paper, there's diagrams as to like sort of what an EEG like cap or what the capture device looks.
You know what it looks like? It looks like the Black Mirror episode where the guy can feel other people's pain. You know what I'm talking about?
Yeah,
we'll show that in the video.
So yeah, the electrodes are placed on different locations of the head, right? And so that would be a spatial relation where the electric signal is coming.
And then the timing is the...
In time, it's a sequential signal.
Nice. Okay. That makes sense.
So we wanted to use transformers.
Could you, before you go into that, I know you've talked about like where transformers are used. Is there like a quick kind of definition on transformers that would like help us
on what a transformer is?
Yeah, or maybe it's better just like what it does or what it is.
Like I guess even like AI models. If someone were to say, "Oh, it's an AI model," like what that means is there's inputs, right, and then there's an output, and in the middle you could call that the model, and it's doing math. At a very high level. It's a black
box of math.
Yeah, at a high level, it's doing math. You have inputs and outputs. That's the model. So a transformer model is a type of machine learning architecture, and it deals with sequences. So text is sequential.
Like something after the next.
Yeah, a sequence. So in language, you have words that construct sentences, and each word is a part of the sequence.
Okay.
So
with a video, it's a sequence of frames.
video, it's a sequence. So, and biosignals are also sequential data.
Mm-hmm.
So I guess you could go into so much detail as to what transformers
That
are.
makes sense. But they're good at capturing sequences and analyzing them with the map.
Yeah.
My question is, this is kind of off topic, but that seems like the major scope of all AI we see, like ChatGPT, it's built on transformers. What would it be bad at from an AI standpoint? Like classifying images, it's not really sequential, so a transformer is not really useful in that sense.
Yeah, but I mean, images are interesting because you could make them sequential, like videos.
But what about standalone images?
But you could, like, let's say you took a standalone image and created it into tiles, right? So then you could you could split an image into four parts, and then maybe that's your sequence.
Okay, so
if you want to use a transformer, it needs to be sequential. So it needs to be.
Okay.
So
are they really useful in all applications of AI?
Well, if you can transform a problem into a sequential input, then it would be
okay.
Yeah.
Great. So we were.
Yeah. So I think I was sort of just giving a high level. I think maybe. So a part of it, when you write a paper, your paper is contributions. So why is this significant? What makes it unique?
Yeah.
So there are 3 contributions that my paper made. So the first contribution, it was the first time someone had performed EEG-based cognitive load classification using mass autoencoding of features. And so this was unexplored. This was something.
Does that mean that EEG, the cognitive load, that was unexplored, or also the masked feature?
Yeah, all of it. So people had done research into using EEG to classify cognitive load. That had been done. No one had also used masked autoencoding of features to do this.
And the masked autoencoding.
Yeah, so we can get into it, but I'm just saying these are the 3 contributions. So it's the first time that someone did it. And then, sorry?
Congrats.
Yeah. And so the second one was the method used transfer learning between emotion and cognitive load. And it showed that pre-training on our model in a self-supervised manner, which we'll get into, on emotion, and then using transfer learning with frozen weights, and we'll get into that too. It showed that this was a viable path to classify cognitive load.
Why did you pick cognitive load?
So I can get into why. And then so the last contribution is that the model achieves strong results on cognitive load classification, suggesting that transfer learning between emotion and cognitive load, again, is a viable path. So if you were to just use just cognitive load data to classify EEG, like if there were no transfer learning used, it showed that using transformers improved the accuracy. So it actually was useful.
It was beneficial.
To use training, and it achieved strong results. So comparable results to other papers or other methods in this area. So those are the 3 contributions. And I guess going back, so I think we should just give a little more context as to guess how it all started. So I did my master's of engineering right after I graduated with my undergrad in computer engineering. And I did an MEng, it's called. There's that where it's course based, so it's 1 year. You just have to complete credits. The other options to do an MASC, a Master's in Applied Science, which is research based. You're required to do research, have published papers, and it usually takes like 4 years.
Wow.
So after the first term of my master's, first term I just took courses. And then I thought it would be a good idea to, instead of take a course or 2 courses, you can do research and substitute of the courses.
Was that like an equal amount of time, you think, or you would have?
No, it wasn't. But I mean, it was a lot more rewarding.
That's awesome.
And it was a great idea if anyone ever thinks about doing it. So I thought about doing it, and then I reached out to some professors. And so the professor I worked on this paper with is Professor Ali Atamed. And he said, I expressed I had a lot of interest in autonomous driving. I said, I'm interested in this, I don't know. And he said he was actually doing a project that was collecting EEG signal in a driving simulator. So he showed me the driving simulator. It was all cool. That's how it started. And he gave me the idea. He said, this is something that's unexplored, EEG cognitive load classification. We have this data set that we're collecting. I think you should try to use transformer architectures to classify it. That was the idea. I mean, a lot of things came out of that. Like from the title, you see we found self-supervised pre-training, mass autoencoding. So it all built off the original idea of transformer architectures to classify cognitive load. So I think where we came from this. So I worked with Professor Atamed, and then this PhD student, her name is Prithila, also name on an author of the paper. She collected the CL Drive data set. And so she was very helpful in the process.
So her name's on the paper because of the data set she collected.
Yeah, but she was very helpful with me in terms of helping me with everything. We met multiple times a week, and
okay, so
she helped a lot.
Her ability, you couldn't have done it without the data set.
Yeah, and her with her support, she was very helpful throughout the whole process, and same with Professor Atamed. So both of them, they were very helpful in the process. I wrote the paper, but they were very helpful. So that's why they're, yeah.
All right, so few questions we had.
Yeah.
So you kind of touched on this a little bit, but this paper ultimately is in the field of psychology. It's the intersection between psychology and machine learning, right?
Yeah.
So if you were to hand this paper to a psychologist, what would they be most interested in? What?
Yeah, I don't know. Again, like I really don't know much about psychology, so I don't know what they would be interested in. Like one thing that we sort of talked about was the relationship between cognitive load and emotion. I think maybe that's something they would be most interested in. So we can briefly talk about that if you want.
Yeah.
So the idea is, and we sort of talked about it, is transfer learning. It's better when the pre-training task is related to the downstream task. So in this case, I thought of the idea, right, but it was probably only going to be successful if they were related. So you can do research. I did research to see if there were other papers that showed the relationship between the two. And so there's related work in the field, and it's reference 22 and 28 in the paper. And so what one of them suggests, the title of one of the references is 4 ways of considering emotion in cognitive load theory. So again, cognitive load is a subjective measure. You ask someone what their cognitive load is, and they'll rate it on a scale from 1 to 10.
Yeah.
High cognitive load is from 6 to 10, and low is from 0 to 5. So it's subjective. And so what this, I mean, just looking at the abstract of the paper, so they say 4 ways of considering emotion and cognitive load. The last one, which I thought was most intuitive, the final perspective is that emotion affects motivation and in turn, mental effort invested. So
because your mental effort is based on how motivated you are.
Yeah. So, and you could see why emotion and effort or motivation would be related, right? So
Makes sense.
If you're happy, you're going to be more motivated. So that would be, I guess, an intuitive way that would explain why emotion and cognitive load are related. One of the other ones was, let me see. Yeah, I don't know. So that sort of gives an idea of why emotions and cognitive load would be related.
Cool. That's awesome. I think we've talked a lot about like the psychology side and emotion and cognitive load. Maybe I think probably a lot of listeners are really interested also just like the times, like machine learning and AI and everything.
Yeah.
And I know like the phrase came up a lot of like self-supervised math.
Yeah. Okay. So that's a good way to go next. So in machine learning, there's 3 types of learning. Mainly, I mean, there's others, and people are doing research to find other ways of doing it, but these are the 3 main. Supervised learning, unsupervised learning, and self-supervised learning. Supervised learning is when you have a task and a data set that's fully labeled. So the example of cats and dogs, this would be an example of supervised learning. You have a data set of 1,000 images that are all labeled with cats and dogs. Someone looked at the images and said
cat or dog.
Cat or dog.
Like it actually means like they put a box around it.
Yeah, or even they just like...
Or they named the file.
They named the file cat. Okay, so that's a way of labeling it. This is supervised. And so what happens is the machine learning model it makes a prediction as to what the input image is. So it'll make a prediction. Let's say it predicts dog, and the answer is dog. Then the error between the correct answer and the ground truth, or the ground truth, the correct answer, and the prediction of the model, that would be a correct answer. So then the model learns from its mistakes. So let's say it gets it wrong, right? So it's learning from...
And it makes adjustments?
It makes adjustments. It's learning from the supervision of the labels, the ground truth.
Okay.
So that's what...
You know what's right and you know what's wrong?
And it makes corrections based on the supervision.
Okay, and so what's unsupervised?
Unsupervised learning would be a way where you take data that's unlabeled. So there's no label associated to the data, but the model is still able to learn relations in the data. And so a simple example would be if you think of data scattered on an XY coordinate system. And the data, it has XY pairs, right? And it could describe anything. Let's say it could describe cats and dogs, right? So the X could be the color of the cat, and the Y could be the age of the cat, right? It could be any data, but it's not labeled. It's just XY points on a plane. And unsupervised learning would try to fit a line that separates the data points, which you could use to classify a new data point or the given data. So let's say if you were trying to classify cats and dogs, the data would be linearly separable, right? If you visually saw it, the cats may be in the upper right and the dogs may be
so it's on either side of the line. That's how it's classified. So how does it know if it's wrong?
So what it will do is it's just trying to group. It's trying to group the points into 2 separate groups or fit a line that best fits it. So it will update the line will update based on a given occurrence and the distance between the line, right? And so it'll correct itself in an unsupervised manner to fit
by fitting the line.
But
so that's how it sort of learns, by fitting the line.
Yes.
But when it's all said and done, how does it know how accurate it is?
So you could give it a new, to test the accuracy, you would give it a new data point and see what it predicts it.
Okay, that makes sense. Okay, and is it always a line that they use to test it, or were they use like a squiggly line?
So exactly that. This is just one example of what unsupervised learning is. The idea is that the data is not labeled. Okay. That's the idea.
And then, so what's self-supervised?
Self-supervised. The most famous example of it is how ChatGPT or how large language models were trained. And the idea is that the data itself, you can create labels from the data itself. So the example would be in a sentence. This is what you could call masked autoencoding is. If you have a sentence, you mask out one of the words.
Like you hide it.
You hide it. You take it off. So if the sentence is "we are recording a podcast," and you take out recording, so it's just "we are blank a podcast." So you mask the word, and then that word becomes the label. So the task is to predict the missing word in the sentence, and the label is the word. So if you take a Wikipedia page and you take all the sentences in the Wikipedia page and you randomly mask one word in each sentence, and then the task of the model is to predict what the masked word is. And the self-supervised idea is that humans, we're not required to label this data. The label is coming from the data itself, right? You don't need to give the sentence to a group of people to then label those sentences. It's self-supervised, it's self-labeled.
Okay, so what about your data was self-labeled?
Yeah, so that's how it's done. So the idea is that you take all of this information from the internet, the ChatGPT example. Take all the information from the internet, randomly mask words and sentences. And the idea is an example, we are recording a podcast. If the models can correctly identify the word recording, it would indicate that it understands like maybe what a podcast is, right? Like a podcast, the probability of that missing word, it's probably recorded. Like from our intuition of it.
So is it like the label in that case is actually just the context in which that word would be used? So in that case, recording, it's like this label represents the context in which recording would be used.
Well, the label is the word. The label is the word. It's nothing more than that. It's just the word.
But it's being like, the understanding of the system is like, this is a context with like, I know.
Yeah, but the masked word could be like a filler word, right? Like it may not have meaning in the sentence. So that's also.
But does that make it worse?
It's just the nature of how it works. The idea is that you're training the model in the sense that if we mask a word out, try to predict what it is in terms of the sentence. And this would be a way that we would probably maybe learn how to read when we were young, you know, like and the other task is instead of predicting a masked word, it's predicting the next word, right? Mm-hmm. So it's a way that the model trained on all this data. And because there's so much data and it's self-supervised, you don't need to label all the data. You're generating labels from the data itself. So that's why it's possible, right? Because we can use all this data and it doesn't require manual labeling, which would be a supervised fashion. And so the idea is that in the pre-training task, the masked word prediction, the model is to gain a general understanding of how language works, right? And by doing this, like the example, we are recording a podcast. If it's able to know that it's recording, it generally understands how language works and, you know, the concepts that recording and podcast are related. And so the idea is to get a general understanding of language from this task. And it showed in natural language that this is very powerful and it works. So in my case, the masked feature autoencoding, we took that idea and we took a signal of EEG. And instead of masking a word, you could think of so we segmented the EEG signal. So you take an EEG signal and you segment it into, you cut it off. There's an image in the paper that.
But you're breaking up into different frequencies.
Yeah. So instead of words, we have segments of EEG signal.
Okay, and that's comprised a sentence.
Yeah, and
that
instead
like a
of
set like length of
yeah.
time.
So if you go to the yeah. So here in the post processing EEG signal, you can see the signal in the back and you can see the segments there, right? So that's what it would look like. It's
cool. Okay.
And so the segments are the words, and the the segments create a word, a sentence.
A sentence. Okay, that makes sense.
So we took the idea of masked word.
Yeah, now you're masking one of the signals.
Now I'm masking the signal. So what we did is we masked and we tried different how many segments you create, the length of segment. We tried all of those things. Each sequence is comprised of 3 segments of EEG signal, and one of the 3 segments is masked.
Okay.
And so then the feature part of it. And what this sort of is like, you could take the raw EEG signal, and what that would look like is just, there's frequencies, right, in the EEG signal. So, you would just have basically the voltage output from that electrode, right? And so you could take the raw signal, and that has a lot of dimensions. It has a high dimensionality. So
that means what does that mean?
It would mean, so let's say there's 10 electrodes on the EEG cap, and you're taking the raw signal, then you would have like 10, if you think of it like a table, like an Excel table, you'd have 10 rows, right? And they all have values. So that would be, if that data, that input data would have high dimensionality. And so it gets more because each electrode has 4 channels, right? So then if you have 10 electrodes, all with 4 channels.
Okay, it's getting crazy.
It gets crazy. So the idea, you could refer to it, it's a curse of dimensionality. Sometimes in machine learning, if you have too many dimensions in your input, it's cursed. The output isn't going to be great. So instead,
it's not always more is better.
Yeah. So instead, we use features, and a feature, you could think of it like a feature of an image or a feature of any data set could be like the maximum of it. That's a feature.
It's like
min, standard deviation.
It's like not a description, but some sort of
extracted metric.
Exactly.
Yeah. So we use features, and what the features we use, one was called PSD, power spectral density, and the other one is differential entropy.
That's like how strong the signal is, the power spectral density.
Yeah. So we use these features instead of the raw signal. We use features. And
so you're not even analyzing the whole signal. You're just analyzing features of the signal.
So with the segments, there's 3 segments in the sequence. Each segment would have a feature, a PSD feature, that describes the PSD, the power spectral density of the signal in that segment.
So it's because you need something to be able to compare them to each other simply.
Yeah, sort of, yeah.
So going back to the cats and dogs example, it would be like, instead of looking at the whole picture, it would just be looking at the color of the fur or something like that.
Yeah.
To make the guess.
Yeah. So
the classification.
So we use features. That's mask feature encoding. So we're masking the features. So instead of masking a word, right, we're masking a feature. So,
and that feature that you're covering becomes the label. Of that signal.
So can the model take the other 2 segments and take them and say, how are they related to the missing one? And what's my guess of the PSD value of the missing segment?
Gotcha. So you're looking at the PSD, part of it, you don't know what it is, and you're looking at the other parts of it, and you're saying, okay, is it this type of signal or is it another type of signal?
Yeah, high and low call.
And then high or low, and then over time it learns.
So the pre-training phase is just doing this mass feature prediction.
And does that actually end up looking like in numbers? It's like it'll be like 257, and then it's like
it's
a 27, and it can be
really simply that's what it would look like. Okay. Segments would be just a number, and then you mask one of the numbers out, and so it'd be like 527 mask 2. So you have 5 and 7, and so then it makes a prediction as to the correct prediction would be 2.
Cool,
just like that. And the idea is that in the pre-training phase, like language, it gains a general understanding of what EEG signal is. So that's sort of the concept of the masked autoencoding.
Wow. Okay, that's great explanation. Awesome. That's a very, very well spoken explanation. We have been very technical, but we did have some questions outside the technicalities. Aaron, I know you had a few, but what, like, maybe I'll start with one. If, let's say you were trying to sell this paper to someone, right? Because they needed the information.
Yeah.
Who would be the first person you'd call to buy it? Who's this most useful for? Is it psychologists like you described? Is it people who are looking at the EEG signal classifications? Like,
I think it would be
where would this have the most impact?
Most useful in like an actual application, like we talked about in surgery. I think the most applicable scenario would be a case where it would be easy to wear an EEG sensor, because you're not going to be driving and wearing an EEG sensor every time you drive. You're just not
It's like a seatbelt, you buckle up,
Yeah.
put on your EEG.
So a scenario where it would be easy to incorporate EEG cap would be like a fighter jet pilot, right? Because they're already wearing a helmet. So you could just put the EEG sensor in the helmet. And
Can you only collect EEG signals via these wires, or have things advanced where now they
if you like search up what they look like, I think the one that was used in the CL Drive data set, the one that Cathilla, the PhD student, collected, it was like a headband. So it was just like sort of a headband like this.
Oh.
And it has electrodes in it. I mean, that had a less amount of electrodes. It says in the paper how many, but other caps have 30, 40 electrodes, and it's on the entire head. So it's all like...
So,
Yeah, like the
and you're saying, okay, fighter pilots, we can see, okay, if they're cognitive
You
load
saying the hair?
Yeah, I'm saying like it's crazy the hair doesn't get in the way.
Something that I got into is that there is actually ethical considerations when collecting EEG signal, because hair does have an impact.
It does impact the signal.
It does. So some people say that collection of EEG is so-called maybe a racist, you could say.
Oh, really?
No, but like, what do they not just take it on? I was thinking that everyone was in this study was bald.
No, you don't need to be bald. You don't need to be bald, but hair does have an impact. Like different cultures of people may have different types of hair.
Oh, and that could impact the signal.
That could impact the signal.
So there could be an implied bias in the
Yes.
classification.
So there are papers that talk about the
So, well, so you're saying a fighter pilot, or okay, they sit there, they realize their cognitive load is really high based off their signals.
Yeah.
So maybe they're
alert.
autopilot, or they should go on autopilot, or the other person should step in so they don't make any mistakes.
Yeah, exactly. So that would probably be the best way to implement it, or have its most values in situations like that. And it could be easier in surgeries, right? Because they wear like a cap already.
Yeah.
So it's not like a hindrance to them.
Yeah, and you said that it's non-invasive collecting of these signals. Is there
There are
invasive devices
versions of
and are they more accurate, or these?
I couldn't tell you. I don't know. Yeah.
Okay.
Interesting.
When you were I think a lot of people like we said are interested in machine learning, doing this stuff. Like, what were you like actually doing when you put this paper together? Like, if you had to break down. Like, I was sitting on my computer on VS.
I was plugging into people's brains.
I was sitting on my computer for 99.99% of the time. It's all done on.
And doing what?
You're coding. It's so there's Python. Python's a coding language, and so there are libraries, or I guess I don't know how you would describe it to someone, but there's tools. There are tools that you can use that are specific to machine learning. So you use these machine learning tools.
What'd you use?
PyTorch or TensorFlow. I think I started TensorFlow and then realized.
So TensorFlow does what and PyTorch does what?
They're both machine learning architectures, and I mean, they're ways they're sort of like building blocks to construct models and train models and run inference with models, and so they're frameworks that help you do machine learning tasks. They're tools.
They have a bunch of functions and capabilities that are pre-built to do the tasks that you would need to do
in machine learning. Yeah.
Okay.
So it's just coding, and I mean, a lot of it is also like data preparation. Like that's a big part. Like a common phrase is garbage in, garbage out. Like it's true. And it's like, I mean, if the data is garbage, then the prediction is going to be garbage. So a lot of it is data pre-processing. cleaning the data, extracting the data. So Priscilla was a big help with that because she collected the data, but there's also publicly available data sets. And I mean, a part of it is like, so the publicly available data sets were collected with different EEG caps. So they have different electrodes.
So how do you know that?
So one of the things we needed to do was pick, and there's one of the figures shows like, so this one with the EEG sensors here.
Yeah.
So the figure on the bottom,
figure 4 and 5, yeah,
is it shows the electrodes that we selected from the seed data sets.
Yep.
And you can see that they're in spatial. They spatially are related. So we took the most similar electrodes based on where they're placed on the head. So one EEG sensor was like, let's say, a headband. And it had sensors here, here, and here.
Yeah.
And the other data set was collected with the bigger one, and it had sensors here and here. So we took.
So you only use the ones that the headband also covered.
Yeah, that were most similar.
Like the middle of the Venn diagram.
Yeah. The most similar. So that'd be like a data pre-processing thing that we needed to do.
Okay. So and I was thinking, I was watching a show the other day, and at the end there was like a bloopers thing. What would you say were like if you were the biggest bloopers? Like if looking back, you're laughing. Like I remember you gave me a call once and
it's
you were
not
saying,
really funny, but I don't know if you remember this.
I remember you gave me a call about something like.
Oh, I guess. Okay, so I wrote this last year. We weren't living together. I was living with other people.
By the way, we were all
roommates in
So the idea. So I started writing this in January of last year, and there are deadlines for paper submissions to conferences. And so there was a deadline for a conference, and I had started writing the paper for this conference, and I can't remember exactly what it was, but we were looking at the data, and my professor or the PhD student sort of questioned one of the results. And I realized basically, like, you could think of it like a mistake or something that we overlooked. And it was basically like, you can't submit this paper. So I was like, it's all wrong. It's not like it's all wrong, but like...
Okay, I think also we should add for the listeners that everything ultimately did work out because you won.
Yeah,
you won
at the conference. Context, but the paper was.
How loud were you? Were you like, fuck it?
I was working. I stayed up. I stayed up like really late because I was like, this is insane. Like I need to either figure out if this is actually an issue, or not. Yeah. And I was up until probably like 3 a.m. and I
just
gave up. I just was like, this is.
So how'd you fix it?
I'm struggling to sort of remember exactly what the issue was. I think it had to do with, I don't know if it was how I was collecting I don't know.
I remember you called me once and said that you thought your results were really good and that you hit a threshold.
Yeah.
And then your professor looked at it and said, this is too good, something's wrong.
Yeah.
And the way you're analyzing the results was wrong. And for some reason, you were like 30% more accurate than you thought you were.
Yeah, I mean, there were a million things. So that, like, thinking that, like, you have great results or that you're going to submit the paper and then the next morning you realize you can't. Or, like, you know, like, there was just so many, like, crazy things like that. And yeah, so eventually it was accepted to a conference, and I presented the paper in October of last year.
Where was it?
In Paris, France.
So did you present it in French?
No, I did not. And so I presented it, and then I ended up winning the best paper award there.
Very nice. Did you get like a?
Well, so I had a ticket to the banquet. And I thought the banquet was on the Friday, and I had a flight out, so I knew I was going to miss the banquet.
Yeah.
But I was wrong, and the banquet was Thursday, but I had already given up my ticket. So I didn't go to the banquet.
And you won the award.
And I won the award. And I had no idea. and then 2 months later, I got an email saying like, oh, like, by the way, you won the best paper award.
That's hilarious.
So I didn't go to the thing because I picked the wrong, I thought it was on a different day.
Well, they wouldn't let you in? Was like that?
I didn't know. Like so like Friday morning, I realized that it was actually last night. I didn't know. I didn't know.
Funny.
Yeah, so that was all.
So now, just moving on, you've written the paper, published. Okay, that portion is done. And are you still using any of this? I know you're a machine learning engineer. Are you doing similar research? Are you advancing on this in any way? Has anyone reached out to you about this paper? What's going on since this has been published?
Yeah, so I mean, I think that the bigger thing is just like the learning experience of writing a paper. Like it was the best learning experience I've ever had. And I did learn a lot about like machine learning and transformer architectures, which now in natural language and chat GPT, and that's, I mean, in all business cases, it's the most applicable thing right now and everyone's doing it. So I do a lot of it in my job. So I gained, I guess, experience for transformers in general. So I do use some of that in my job, but we're not a research group. We make internal solutions for Verizon.
Yeah.
So I don't directly use any of this. I'm not doing work with cognitive load or EEG within Verizon. It would be something I would be interested in doing in the future, but yeah.
Okay, great.
I had one question that's a little technical, like in the weeds of it still, but it's like, what like math did you like have to use in this? Like, what would someone need to know to be able to really understand the paper math wise?
I mean, that's an interesting question. Like, I didn't do any math. I didn't like.
I guess that the libraries were doing the math for you.
Well, it's just like, so like we said, like these models are, you know, if you go into depth into what a transformer architecture actually is, then you'll understand the math, and you need to understand the math to understand what's going on.
I remember it being a lot of matrices. Is that correct?
Yeah, that is what it is. It's a lot of multiplication.
Yeah,
it's a lot of multiplication.
Like 3D, 4D matrices multiplication, or just like more simple ones?
It's just it's simple. It's, I mean, at the very core of it, it's just a bunch of multiplications. I mean, not actually, but like, I mean, I think that it would take, I mean, you'd need like a whole like deep technical dive into transformers to understand the math work, but it's really interesting. And there are other examples like convolutional neural networks where I think it's easier to understand the math because you can sort of visualize it. I don't know if you want a little explanation. Is good. Maybe this would give a better idea of how the math is involved, but in CNNs, the convolution it's a windowed operation over the image. So you have an image and these convolutional layers, they do a windowed operation over the image, and each time the window, let's say it's a 4x4 grid, and each value in the grid is a number. And so you take the grid and you multiply those numbers by the pixel values. And the idea is that the convolutions, the numbers in the window, they can be constructed to extract things from the image, like lines, edges of the image. So if you pass a window or a filter over an image with certain numbers and you multiply the pixels by those numbers, the resultant image, or what that would look like, is it could be just the edges of the object. So the idea is that you do these mathematical operations that is just multiplication. You're just multiplying the window.
How does multiplying a number by another number allow you to find
lines or something like that?
Yeah.
So
like a gradient, like a change?
No, it's not. It's a little simpler than that. It's just, if you think about it, like pixels, so an image is 3 channels, red, green, blue.
Yeah.
So you can think of it like a cube, right? So there's red, green, blue is the depth. Then the height and the width is this size of the image. So each pixel has 3 values, red, green, blue. So if you like, I don't know, if you take like a book and the background's a white wall, or like that image on the wall, right?
Yeah, it's like a picture against a frame.
So the edges of the frame, on one side of the edge would be zeros, would be white, right? Mm-hmm. And the other side of the pixel would be
the values. Okay.
So
this makes sense.
So if you were to take a filter, right, and let's say it's ones and zeros. So it's like, let's say a 4x4 grid, the left values are ones and the right value are zeros. And if you were to do that operation on one pixel on the edge, right? So you multiply one pixel by these values. And so if you were to multiply, or if you think a better one would be like, right, like a 3x3x3 grid that you're multiplying. And the middle line is ones and the outer lines are zeros.
Yeah.
So if you multiply the edge, right, then you would just get, on one side would be white and the other side would be zeros, right? So you're getting 0, 0, that's white.
And in the middle you're getting...
Yeah, so you can extract representations doing things like that. And it's easier to visualize it. It's sort of hard to explain, but that's, I guess, how math is used in these AI models.
So it's mostly like algebra and matrices.
Yeah.
Else. Yeah. Cool.
Do you have any other questions?
I think that's mostly what I was interested in.
Awesome. All right. Well, Dustin, it's a pleasure having you. Look forward to seeing what you do with your masked auto encoding in the future.
Yeah. So it was great. Thanks for having me. And again, I gotta give credit to also my professor, Ali Etamed, and my PhD student, or not my PhD, so the PhD student I worked with, Priscilla. They were very instrumental in the creation of this paper. And so give them the credit that's due. And
of course.
Yeah.
All right. Well, thank you for joining us.
Thanks, Dustin.
Thank you.